Here's an advantage of additive manufacturing we haven't talked about. 3D printing is potentially a solution for super tiny parts. We go really small on this episode of The Cool Parts Show.
Season 3 of The Cool Parts Show is brought to you by Carpenter Additive. The company's Athens, Alabama Emerging Technology Center is an end-to-end additive manufacturing production facility with everything from materials development through post-processing under one roof, ready to help you with your next metal 3D printing job. Check them out at carpenteradditive.com. Now, back to the show.
I'm Pete.
I'm Stephanie.
This is The Cool Parts Show, our show all about cool 3D printed parts made by manufacturers, maybe manufacturers like you.
So 3D printed parts, but I'm getting the sense this is another one of those surprise reveal episodes because there's no part on the table, Pete.
I brought a part. I brought you many parts. Here is an advantage of additive manufacturing I don't hear talked about much at all.
And you said parts, not part, and I still don't see them. Where are the parts?
Take a look in your coffee cup where I have brought you 500 3D printed parts.
So this is not what I usually drink in the morning.
Additive manufacturing is a potential solution for making tiny, tiny, tiny parts and possibly presents an easy way to do it.
Okay, so that's interesting because I feel like one of the challenges with 3D printing that people often point out is this issue of resolution, right? And how small can you go, how fine of features can you do? But you're saying that 3D printing actually is the right solution for these tiny little parts.
Potentially. These are tiny little electrical connectors. Tiny little connectors for a very compact electronic assembly. They were made by Boston Microfabrication, BMF, and a part like this, if not for 3D printing, would otherwise be made by injection molding. And the prospect of making a mold that tiny with features, cavity, core that tiny, that precise, it can be done. Companies do it, but it's challenging, and a mold like that is expensive.
Okay, so I see the appeal of getting away from tiny little molds for parts like these, but the 3D printing method is not entirely obvious. So Boston Microfabrication, what's the technology that they're using?
Right. So BMF is doing DLP, digital light processing. So a bath of resin and optics cure an entire layer, one layer at a time. It's not a point-by-point process. There are other 3D printing makers who use DLP, but they use it for more macro-size components. What BMF brings is that they add a couple things to the machine. One is there's really precise XY motion. And in fact, the bed of resin is what is moving in X and Y, so the optics can stay stationary. And that bed is descending minutely, layer by layer. Other DLP systems kind of orient that so the part is suspended. We'll talk more about that. So precise XY motion combined with very precise optics to form the part. This is John Koala. He is the CEO of BMF, and he has a little more to say about that.
Getting fine resolution is depending on the process, right? So if you're using FDM process, it's often about the nozzle size. If you're using a laser-based process, it's often about the beam width to be able to get the resolution that you're looking for. In a DLP process, it's really about the image resolution, similar to when you're looking at your television. The higher the resolution, the sharper the image. And so we're using a 1080p DLP projector. But then we're also using a lens to really be able to focus that resolution down even finer, down to the 10 micron optical resolution that we're really looking for. So that's the key to get the pixels to be small and the resolution to be where we have it for high performance.
Okay, so that kind of addresses my question about resolution. It's a combination of that projector and then the lens that lets you get that really fine detail.
Yeah, so that's what achieves what they call microscale 3D printing.
Okay, microscale, what do you mean by that?
Right, so parts and part features that are really, really tiny but still visible, right? So we're not talking about microscopic work necessarily, we're not talking about nanoscale work, but we're talking about features that fall in the realm where these parts would otherwise be produced through micro injection molding or micro machining, and put a pin in that because there's a micro machining related solution we'll get to too. But it's not just for tiny parts like this, not just for that, because there are also features of larger parts where this could make sense too. So here's a more macro scale part, and at a glance you might think that like this makes sense for a more macro scale 3D printer. This is a chip socket, but if you look closely, you can see there's this array of tiny, tiny holes, and those tiny holes in this case are the feature that is produced through the microscale 3D printing.
Okay, so this is a solution not just for these tiny little parts, but also for larger parts that have fine features or things that would be maybe difficult or challenging to injection mold, for instance.
Yeah, applications. Tiny electrical connectors, tiny little medical components, microfluidics parts, and also just prototypes for parts that are really, really tiny. If the process and the tooling is really hard for a part that's ultimately going to be made through a conventional process, it still makes a lot of sense to use 3D printing to get that part design just right before you have to make that investment. And prototyping is where BMF initially saw the promise of this technology and what they've addressed so far, but they also recognize that on a cost comparison basis, for some production applications of really tiny parts or parts with really tiny features, yeah, maybe this 3D printing platform really is the way to go.
Okay, so you mentioned cost savings, and sometimes we talk about additive as like reducing the amount of material that's used, but there's so little material here to begin with. I feel like the cost savings is probably more from the process side, right?
Yeah, good point. In conventional manufacturing, little creates big challenges. The injection mold to make a part this tiny, those tiny little features machined really precisely into the mold. There are companies that know how to do that, mold makers who know how to do that, but not a large number of them, and it's challenging work. Similarly for metal parts that are micro machined, in some cases that micro machining is done with cutting tools so small in diameter you can barely see them. And tools like that create processing challenges, handle with care type challenges in the setup and the use of those tools. Again, only so many providers out there, suppliers able to do that kind of really fine, tiny work. But a 3D printing process that has the accuracy and the resolution and the fineness built in, by comparison, it's a relatively easy way to produce these tiny parts or parts with these tiny, tiny features. John Koala actually has a little bit more to say about that. Let's listen to him.
Yeah, today for a lot of small parts, for whether it's electrical connectors or whether it's other applications, the traditional, the current methods for making that either are what's often called micro injection molding, it's a subset of general injection molding, or micro machining. So very, very small parts. In a lot of ways, the smaller the part, the more expensive the process. So that's the challenge, is that the tooling that would be required for molding, or the setup and the equipment that would be required for CNC machining, are in some cases an order of magnitude more expensive than if you're just making a standard plastic part or metal part today. So I think the promise of 3D printing is it just makes that easier. So parts that are complex to mold or difficult to mold or complex to machine are relatively easy to 3D print. And so I think that the promise is that this technology can displace some of those traditional methods for manufacturing.
Okay, so the thing that's kind of striking about that is that a lot of 3D printing processes, and DLP is one of them, involve support structures. And so once you finish the print, you've got to somehow remove those support structures. How do you do that with these tiny little parts?
I'm so glad you asked about that. So I mentioned how their system has the build platform descending minutely. The part grows up from below. In the resin bath, the buoyancy of that resin, because these parts are so tiny, so fine, just that buoyancy provides just enough support. In many cases, the float is enough to sustain the parts, support them so no structures are needed.
Okay, so no support structures. That is really cool.
Yeah, yeah. So let me show you another example of a part. Here's a case where the microscale 3D printing potentially can replace a metal part. This is a glaucoma stent. And conventionally, right now, it's made of titanium. It is micro-machined, and the potential 3D printed replacement is made from a biocompatible polymer. Right now, this stent requires 2 surgeries, one to put it in and one to take it out. The biocompatible alternative potentially dissolves in the body, eliminating that second surgery.
Oh, wow. So changing the process allows for this material change, which completely changes the nature of this surgery. It makes it so much easier.
Yeah.
Okay, so you've shown me a couple of different applications now. The glaucoma stent, this connector, the chip socket. What other parts can this be used for?
Yeah, so potentially different sectors, different applications. What BMF is really thinking about now is the next step, I think, is moving into production, using this platform as a possibility for repetitive manufacturing of these tiny, tiny parts. Here's John Koala one more time.
The platform that we have today, we think well serves prototyping needs. We've got a range of materials that serve those needs well. We think the speed and the productivity of the platform is quite good for prototyping needs. But when you're really moving toward production applications, you need to do 2 things. You need to check 2 boxes. And those boxes are, 1, the part itself needs to match the requirements of the end part in terms of accuracy, surface finish, detail. We think we've already checked that box. The second is material properties. So the material needs to if it doesn't match 100%, it needs to be good enough or close enough. So mechanical properties, thermal properties, perhaps dielectric properties, depending on the application. So that's the second box to check. And we're working on that with both internally on the material side and with partners to develop materials to match those production materials. And then the third one is speed. So if you're trying to take a 3D printing application and use it to displace a current traditional manufacturing method, the economics need to be there. Perhaps you can pay a little bit more for the convenience and not having tooling and inventory and the promise of distributed manufacturing, but it can't cost much more. And so it needs to be able to meet the economic requirements of the customer. And that, in a lot of ways, comes down to material cost, it comes down to equipment cost, and it comes down to speed. And I often think that speed equals money. I mean, if you have a slow machine, it just means you need a lot of machines, which may not be economical. So when we really think about what needs to happen to sort of move this technology forward, it's materials development and speed. And those are both things that are on our product roadmap.
Okay, so one thing that John mentioned that we haven't talked about yet is speed. So you said there are 500 parts here.
Yeah.
How long did it take to print these?
Sure. These were printed in batches of 150, about 2 hours build time per batch. So do the math there, 500 parts, something like 7 hours.
Okay, so 500 parts in less than an 8-hour shift.
Yeah.
Pretty cool.
Yeah.
Okay, so I think I got this.
All right.
These parts are connectors. They are in a range that we would call the microscale. So they're not microscopic, they're not nanoscale, but they are very small, very detailed. They were made by a company called Boston Microfabrication, which uses a very high resolution DLP process to print small parts like this and other parts with fine features. This is a cost-effective solution to micro-injection molding or micro-machining, and it has a lot of diverse applications, everything from the medical industry to optics to electronics.
Exactly right. I think that'll do it. Thank you for watching The Cool Parts Show.
If you want to tell us about a cool part that you're making, email us, coolparts@additivemanufacturing.media.
If you've just found us, if you're watching us for the first time, you can go back and watch all of our existing episodes at our new URL, thecoolpartsshow.com.
And if you like this show, we hope you'll subscribe, leave us a comment, and tell a friend. Thanks for watching.
Thank you.
Thank you to our sponsor, Carpenter Additive. Listen to additive manufacturing podcasts, attend webinars, and learn more at carpenteradditive.com.